Hello, and thanks, Thomas, Elio, and Laura for the invitation. It's very nice to be here. Um, uh, my title says it all, but if you want to, I mean, if you have too much wine yesterday, I want to give you the take-home message of this talk, which is that if you have, under quite general assumptions, first-order Mott transition, you will end up having at finite doping quantum critical point emanating from this first order transition. And I hope I'll convince you about this in a specific setting, which is one of the Hund's metals. We will first start in a simple model, and then we will work our way up to iron-based superconductors, which are today our main, one of the main frameworks in which the Hund's metal concept is relevant. I will show you a couple of spin-offs. So research connected to this one, but slightly separate. If time allows, two, otherwise just one. So let me first acknowledge the fact that this work was done by some very bright young students. Maria Hassi Lefteriou, it's the first part, Pablo Villar-Arribi, and Matteo Crispino and Tommaso Gorni, who was a postdoc in my group. And then in collaboration with the Würzburg group, with the Trieste group, and some other people in the spin-offs that I will mention if I get there. We'll be analyzing a multi-orbital Hubbard model in which the one body part is a model in the beginning, so just diagonal hopping, two orbitals, just hopping intra-orbital, but this can come from a tight binding coming from a DFT calculation for a full material, as we will see in the following part of the talk. Then the interaction is a local Hubbard-like interaction with intra-orbital, interorbital, and exchange part, which is measured by this coupling J, is the Hund's coupling, and embodies the fact that the electrons like to be on the same orbital with spin aligns, and if possible in separate orbitals, which is typically a fraction of the main coupling of the interactions, which is the Hubbard U. We use dynamical mean field theory or Slade spin mean field, which is a simplified way to solve the equations in the spirit of dynamical mean field. The main results about this two orbital Hubbard model with degenerate bands and Hund's coupling is that you have a Mott transition at half filling, which is here depicted by looking at the quasi-particle weight that at zero interaction strength is 1 and then goes down, showing the degrees of metallicity, and when it vanishes, you have a Mott transition. Now, the message of this figure is that as soon as you have Hund's coupling, this transition becomes first order. So there is a jump. And this is true for the density-density interaction that we're using, but it also holds true for the more realistic Kanamori form of the interaction. This is seen through many different methods. What we will do is we'll clean up very well this issue by solving dynamical mean field theory here with numerical renormalization group, which really captures the physics at low energy very neatly. And we have cross-checked all our results with continuous time quantum Monte Carlo and exact diagonalization. So in a symphony of methods that it's really coherent, and we can enter into this if you need. So what is interesting is that how does this jump happen? This jump is a jump. Here we see the lower part of the previous curve in which Z is vanishing in this branch, which is metallic. But before jumping to this red branch, which is Mott insulating, you see that actually that there is an unstable branch connecting the two stable branches, which is still metallic, and so goes back in, has Z going back in U. So you can say that there is a folding of this structure of solutions, which in the end, of course, means that if you scan the parameter space, you will jump from this solution to this other, or if you go back, you will have what we call a coexistence zone of solutions. But really, the structure of solutions is connected through these, adiabatically connected through this unstable metallic branch. Now, this is interesting also when we look at the results doping the system. So this was at half filling. Now let's let's go out of Alfvén. If you dope the system in the zone where you have both the metallic stable, the insulating stable, and the metallic unstable solutions, the metallic solutions will be immediately doped once you move the chemical potential, whereas this plateau is the Mott plateau that you get when you try to move the chemical potential in the Mott insulating solution. You have a gap, and only at a finite chemical potential you get doping. Now, what's interesting is that if you increase U, you will keep having this structure of connected solutions, which then unfolds slightly, and in the end you get at some given larger U than the U where the coexistence was happening, a continuous just monotonically growing solution. Now, what's interesting is that this adiabatic continuity is preserved both in the two parameters of the phase diagram. We are at 0 temperature, I forgot to say. So U and chemical potential, and here the fact that this folding is preserved. I mean, we can collect these solutions and trace a phase diagram. So in the phase diagram you have this metallic part which corresponds to this part at low U, large doping. You have a metallic part emanating directly from the Mott insulator, which is this line here at 0 doping, at half filling. So it's this zone, which is another metal, and if you calculate the quasi-particle weight, you will find is much smaller than this one. So here what you have is a transition between a weakly correlated metal and a strongly correlated metal, which is the proper doped Mott insulator that we will portray later as the Hund's metal zone. And then you can you have a first order jump between these two solutions, because you have this unstable metallic branch. Here is unstable clearly because you have this negative compressibility. This is doping, so in density versus chemical potential, and when it goes monotonously growing, the system is stable, but when it goes back, it has a negative compressibility in this dashed zones. So it's unstable. So you get phase separation. Actually, you can do a Maxwell construction here, and you will find this zone of phase separation. And when the line straightens in this point, you have a quantum critical point with infinite compressibility, which actually emerges out of the phase separation zone. So this is a generic phase diagram in which what you will be maybe able to see experimentally is this part, this quantum critical point, this transition abruptly with a zone of prohibited doping between two different kinds of metals. And here in the part which is beyond the quantum critical point, you will get a crossover, so in which you will have an enhancement, not a divergence of the electronic compressibility. This can be seen because how we have connected this adiabatic continuity and the folding of the equation of state here at half filling with the same phenomenology that we have in out of half filling, and it's actually can be seen in a three-dimensional way, if you like, as a generic folding of the equation of state due to, for instance, this curve is we are plotting here the Z and here the doping on the same space of thermodynamic parameter, which is interaction strength and chemical potential. This folding of the equation of state that you can see in this quantity and in this other quantity is really the outcome of this curve, which is exactly this one. And if you cut instead in chemical potential, you will have this kind of curves, which are these. So it's a folding in 3 dimensions, and it plastically shows you the fact that if you have this kind of folding at half filling, but you know that very far from half filling, you will have no sign of the Mott transition, you will have no discontinuity. At some point, somewhere, this folding has to have a singular point, after which the equation of state is completely unfolded. So this is where you have the quantum critical point. Now we will see afterwards how this is relevant for real materials, but you can even do a Landau analysis to study the competition between the stable and unstable solutions, and you can do that in Slave spin mean field, in which this Mott transition is portrayed in an auxiliary system of spins as a ferromagnetic to disordered transition. So the order parameter is the magnetization of these slave spins, which is equivalent to the square root of the quasi-particle weight. And you can show through the Landau analysis of this slave spin equivalent equations that the discontinuity, so the first order character, is due to Hund's coupling. So to the fact that the ground state in the charge sector, which is the fundamental charge sector above which you have charge fluctuations in the metal, which are blocked in or substantially reduced in the Mott phase, well, the ground state is split by a small amount, and this small amount is Hund's coupling, and you can actually show perturbatively that these processes are responsible for the first order character that comes up in the Landau theory. And that's very general. You can split the ground state of the charge sector where you create the Mott insulator in different ways, like with crystal field, negative J, and in all cases, you should end up getting an electronic transition of the first order, and all that follows. Now, let me go into the first spin-off. This is really a research done mainly by Thomas Schaffer, by Alessandro Toschi, and Giorgio Sangiovanni along the years, the last 10 years, which nicely crosses our path. So here I'm really collaborating, but it's their main effort. And this connects to the fact, as you have seen, we have here unstable branches, but even if here is like in the van der Waals transition, you have simply a negative compressibility, our compressibility does even weirder things because it's not just negative here, it comes back. So this other kind of unstable branches, it looks weird also because if you look at the compressibility here, the n, the mu, is actually positive in some zones of these unstable branches. So you say, how is it possible that this is unstable if the compressibility turns back positive? And the reality is that we have a space of parameters here, which is u and mu, and it's the condition of stability is done by it's embodied by the fact that the Hessian of the thermodynamic potential, of the relevant thermodynamic potential, is to be negative, definite negative, which turns into a condition on the principal minors of this Hessian matrix. So the first minor is actually d square omega in d mu squared, so it's the minus the compressibility. So the compressibility has to be positive, and we know this. But the second condition is a condition that implies not only the compressibility, but also the derivative in u of the generalized double occupancy, which is the conjugate variable to u in our Hamiltonian. So we had u and j as parameters of the interaction, but j is proportional to u. So there is something multiplying u, which is conjugated to u, and we call it generalized double occupancy. This has to have a derivative in u, it has to go down in u, so it has to be negative normally. But when it's positive, then you're violating a stability condition, even if the compressibility is positive, and that's exactly what's happening in these branches over here. Now, what's nice, what would be nice is instead of analyzing all these derivatives, to have a criteria, a local criterion to know if the solution is stable or unstable. And this is exactly what comes out by analyzing this quantity that it was studied along these years by Thomas, by Giorgio and Alessandro, and I will signal this is also the work of Matthias Reitner and Lorenzo Del Re, and they have there is a nice poster where these calculations are shown in more detail. So I urge you to go look at that. So if you look at the static local charge susceptibility that you can calculate directly from dynamical mean field theory, you can express this as in very generic form as a ladder summation of irreducible two-particle vertices. And in this ladder summation, indeed, in the end, you have always to sum up the bubbles, and these bubbles are then end up as a sum over two frequencies, internal frequencies. Now, if you analyze the quantity which is before the sum is a function of here we're looking at the static local susceptibility. So we have omega equals 0, and you have the two remaining frequencies which are to be summed upon. And so this quantity, we call it a generalized susceptibility, depends on these two frequencies still to be summed. So you can look it as a matrix in this Matsubara frequencies, and this matrix can be then analyzed and has eigenvectors. Now, they have studied that these eigenvectors are telling you something about the system, among which we have worked out the dependence of the uniform. So Q equals 0 static charge susceptibility, which depends on this quantity, and you can show that how it depends on the values of these eigenvalues. And this is the second condition of stability, also expressed in terms of these eigenvalues. So you can really see that if the eigenvalue reaches some negative value set in the specific case of the Bessel lattice here that we are analyzing this model by some number, but this would be another different number in more realistic models, then you have a divergence in either of these quantities. And indeed, here are the numerical results, here done by Alexander Kowalski in QMC. Here you see the same curves that we have seen before, just at finite temperature. And if you follow the way the compressibility is diverging coming from B to A and some intermediate curves, you will see that it diverges here. And this is the value of one of the leading eigenvalue of that matrix, which reaches this threshold. And indeed, it signals the divergence of the compressibility. So now if you analyze these curves in this sense, going through the positive compressibility, negative compressibility, positive compressibility again, which is this path over here, red is the compressibility, you see that the eigenvalue goes from above to above the threshold. So it's really a local calculation that tells you if the system is stable or unstable. And if you go in another, this is just some lower temperature in which indeed you have this weird positive compressibility branch, but which is still unstable, the compressibility will remain stable, but the eigenvalue will still tell you, going below the threshold, that the system here is unstable. So it's really a calculation where you can do one shot on your solution, and it will tell you if the system is stable or unstable there without having to resort to thermodynamic derivatives. So let me go now to the motivation of our studies of Hund's metals, which are iron-based superconductors. So iron-based superconductors have a structure of iron plane with ligands in between and some cations providing charge. They have typically, I mean, the main structure is 5 bands at the Fermi level of 3D character coming from iron. They disperse 4 to 5 electron volts before renormalization due to correlations, and they have a partial lifting of the degeneracy. So all 5 orbitals participate to the conduction bands, and they host, in typical stoichiometry, 6 conduction electrons. What we have, and this can be studied in many families. I like very much the 1 to 2 family, which is so a family that you can dope in several ways. For instance, electron doping and hole doping. And hole doping brings from 6 electrons towards 5.5 electrons. You can get all the way to the other stoichiometric end members. So you go from barium iron to arsenic 2 to potassium iron to arsenic 2, where you can do also isovalent substitutions. So you can dope from 6 electrons towards half filling, and we have characterized that when going towards half filling, very important things happen as far as correlations of the electrons are concerned. So what happens is here, for instance, portrayed by these experiments. Here we're plotting the Sommerfeld coefficient. So it's telling you how renormalized is the density of states. And so when Sommerfeld coefficient is high, it means the system is very correlated, or at least, I mean, the bands have a high density of states. Now, you know that the system is very correlated. Here we are going through the same phase diagram. So from barium to potassium here, and then substituting potassium isovalently with rubidium and cesium, which are larger cation, and basically decrease the bare bandwidth, so correlate the system even more. And you see that the blue points here are going up and up and up. And these experiments are done in the Karlsruhe group of Christoph Weingast. And if you do DFT, you have these black points. So that's where you know that the compounds are strongly correlated, because these results of DFT are more and more off the more you go on this whole dope side. Whereas if you do DFT plus Leib spin with just one value of the interaction strength, you get this green curve, which tells you that the compound, I mean, correlations are playing the role to get this density of states up and that Hund's coupling is key. If I take out Hund's coupling, all this disappears. So it's really Hund's physics. Another result that we have shown is that this happens because the electrons not only going towards Hal-Filling get more and more correlated, but the system tends to orbital selectivity. So depending on the d orbital character of each electron, 5 minutes, okay, I'll try. They get more correlated or less correlated within the d shell. So you have coexisting heavy and light electrons, and this selectivity is really well captured by experiment. I can't analyze all this, but it comes up in different probes. And so you see the values spread more and more, and this is due to the increasing spreading of the correlation strength among the different electrons in the d shells. And it goes, it's very well captured by theory once again. So you really have the DXY, for instance, orbitals, which are very heavy, and they coexist with other orbitals from the same d shell, which are much less correlated. And the third characteristics, which then, I mean, I elect to the three main features of Hund's metals, is the fact that all this is due to the fact that local moments in the paramagnetic phase, so fluctuating local moments, are growing when you go towards Hal-Filling, and these are constraining the physics in a way that it becomes more correlated and more selective the more you move towards Hal-Filling. Now, my second spin-off, one might be tempted to say, okay, what happens if I go even closer to Hal-Filling? And is it possible? Well, cesium, rubidium, and potassium are the alkalines on the left, so it's hard to, I mean, to go more on the left in the periodic table. So we asked to our friends in Karlsruhe to use chromium instead of iron to introduce more holes. And this is known to do this without touching the structural parameters. And indeed, what is very nice is that we took the most correlated of all these 5.5 iron-based superconductors, which is cesium iron 2 We put some chromium, and they put some chromium, and they got the value of the Sommerfeld coefficient to hit the record for iron-based superconductors, and one of the highest values that you will ever find in the electron system. So we think that this is, I mean, we indicated this road, and this goes of quite well also with theory. We indicated this road as a paradigm to maybe have a new platform for heavy fermions, but just born out of the electrons. So in practice, dynamically, the d electrons are generating the heavy ones, which then coexist with the lighter ones and play the role of the F electrons in the regional heavy fermions, with several possible advantages, like they're not radioactive, or they're easier to find than F elements, but this can be discussed. Certainly might be a new platform. And in fact, these are the experiments that were done on this cesium, iron, chromium, arsenic. And here you see the specific heat, which is indeed shooting up. The Curie to Pauli crossover, a nice T-square behavior of the resistivity. So really showing you that you have a heavy Fermi liquid in this state. And here you have thermal compressibility, thermal expansion. Now, what is happening at some point, which is a missing point in order to have a real phase diagram of heavy fermions, is the fact that at some point magnetism should kick in. And here we know the superexchange will be strong when you go towards Hal-Filling. And indeed, at some point, at some chromium doping, they found a completely different beast, which is this blue curve here with reduced specific heat, with a bump in the susceptibility, with negative thermal expansion, and with a sort of a glassy or at least non-metallic resistivity. So we really, and in theory, we could simulate very easily that we expect a paramagnetic to antiferromagnetic transition while moving towards Hal-Filling. So the take-home message here is that by dynamically generating this heavy electrons, so when you take a Hund's metal and you move towards Hal-Filling, Hund's metal tend to be selective, and this selectivity can be extremized. And just before everything is cut off by magnetism, you can have a heavy fermion, and possibly you can go even up to the ballpark of Sommerfeld coefficients typical to heavy fermions. And then, I mean, some different but very similar physics comes when you include non-local correlation, and this is related indeed to the talk of Jan van Telft that he gave 2 days ago. Now, the last part, very quickly, if we go multi-orbit, if we go realistic, you can show, I go back to my compressibilities, and one can easily show in models that the more you go realistic, the more the zone of phase separation due to the enhanced compressibility increases, both if you break any symmetry or if you add many orbitals. And indeed, we could show in all iron-based superconductors that there is a zone that they call a mustache coming from the half-filled Mott insulator, but extends all inside the interaction doping plane until reaching the interesting part where the symmetry breakings and the superconductivity happen. This can be put in relation, in positive correlation with the trends in TC that are found on different families of iron-based superconductors. Here, iron selenium, monolayer iron selenium, or the 111 family. So our message is that this might be this enhanced compressibility might actually be a booster of whatever mechanism of superconductivity is happening in this area, because we always found the high TC compounds to be on top of this enhanced compressibility zone. Now, just to conclude, there is a parallel that you can do with model with for cuprates, where indeed you have the same phase separation zone emanating from the Mott transition, and it's centered where the superconductivity is centered in the experiment, and that's why we manipulate this phase diagram of iron-based superconductors in a way that if you plot the density as average orbital doping, you find something which is very similar to the phase diagram of cuprates, with a Mott insulator, a selective zone that corresponds to the pseudo gap or zone where you have heavy and hot and cold electrons in the cuprates, superconducting dome, and a weakly normalized Fermi liquids at large doping. So my conclusions are here. I will not take the time and just leave it there. Thank you very much.